Hello everyone, my name is Brahim Hilali. I'm working on artificial intelligence techniques for autonomous navigation of mobile robots. Now I'm going to give a presentation of our paper entitled An Efficient Strategy for Optimizing a Neuro-fuzzy Controller for Mobile Robot Navigation. This work is carried out by three authors, Mr. Brahim Hilali, Mr. Mohammed Ramdani, and Mr. Abdelwahab Naji, and will be published in the International Journal of Electrical and Computer Engineering. This presentation will be in four parts. The first is the introduction, in which we present the topic context, the problem statements, and the research objective. The second is the method used to address our problem. The third is the experimental results and the discussion. And the fourth is the conclusion and the perspectives. First of all, what is the context of research? Our contribution is applied on autonomous mobile robot navigation, that is a key field in robotics. It enables the robot to find a safe and efficient path from its starting position to its destination while avoiding obstacles in unknown and dynamic environments. It is essential for many applications such as automated logistics, space exploration, security, personal assistance, and autonomous driving. So, mobile robotics is used in various sectors, for example, healthcare, military space, agriculture, and other sectors. So, what's the problem statement of our contribution? According to our literature review published in June 2023, entitled Neuro-fuzzy Combination for Reactive Mobile Robot Navigation, survey, we confirm the following points. Autonomous navigation faces smoothness and safety challenges in unknown and dynamic environments. Conventional approaches are limited by intensive computation and poor adaptability to dynamic environments. Reactive navigation is an effective solution for dynamic environments, and neuro-fuzzy controllers overcome some of this limitation but face complexity issues. So, what is the objective of our contribution? Through this work, we aim to propose a hybrid strategy for designing a neuro-fuzzy controller for reactive navigation while optimizing the accuracy complexity trade-off, and design controllers that satisfy the constraints of embedded systems, which are limited resource and energy consumption. Now, let's go to the method part, in which we present our efficient strategy for optimizing a neuro-fuzzy controller for mobile robot navigation. This strategy must ensure several features or several advantages, which are the controller reactivity, as the robot must navigate in previously unknown environments, so it must avoid obstacles and reach targets. The equipment simplicity, as the robot is equipped only by 3 sensors to capture the front, right, and left obstacle distance and the target position. The last advantage is the controller optimality, as the controller must have a reduced complexity and high accuracy. To have a global vision, our work is carried out in 2 stages, offline stage and online stage. In the first, we model the fuzzy controller according to the proposed strategy, in which we follow 5 steps. data-driven rule-based modeling, fuzzy set merging, fuzzy rule merging, model parameter learning, and model evaluation. Then we deploy the modeled controller on embedded system for mobile robots. For the online stage, we can use the robot to perform environment perception and navigation in unknown environments. We can start with the architecture used to model our controller in this strategy, which is the adaptive network-based fuzzy inference system. The ANFIS architecture is a neuro-fuzzy which was introduced by Zhang, and it is a neuro-fuzzy model designed to address a variety of challenges, as modeling nonlinear functions and modeling control systems. And it's effective for real-time applications. It is based on the Takagi-Sugino fuzzy inference system, in which the consequent part of the fuzzy rules is a linear function. To understand the ANFIS architecture, we take the following simple case. A Takagi-Sugino fuzzy inference system with two input variables x and y and one output z. Assuming that this system contains two if-then rules expressed as follows, and our ANFIS architecture contains 5 layers. The first is for the fuzzification, the second is for the conjunction, the third is for the normalization, the fourth is for consequent part of the rule, and the fifth is for the diffusification. Using this table, we describe each ANFIS layer. In the fuzzification layer, we use Gaussian function to fuzzify the input variable. In the second layer, we use the product norm operator to conjunct the premise elements of each fuzzy rule. In the third layer, we use the normalization formula to normalize the firing strength W. The fourth layer is used to represent the consequent part of each rule according to the Takagi-Sugino fuzzy inference system. In the fifth layer, we use the weighted average method to perform the diffusification operation to compute the overall output. Other approach used in this strategy is the data-driven rule-based modeling. It consists in modeling initial system from data. The resulting models reflects reality, which is distribution of points. The concept is based on clustering algorithms according to the distribution of data points in space. And each cluster in space is used to assign membership functions and generate fuzzy if-then rule. To model initial fuzzy system from data, we adopt the subtractive clustering method, which is introduced by Xu. This method is a fast one-pass algorithm for determining the number of clusters and their centers. And it depends on the potential of each data point, considering the density of adjacent data points and the cluster radius parameter. And the likelihood value of data points xi to define a cluster center is computed as follows. The purpose of this method is to generate the fuzzy rule base. Thus, each cluster center defines a fuzzy rule. For example, a fuzzy system with n obstinate clusters, n fuzzy rules are generated, and each input variable is associated with n fuzzy sets. After generating the fuzzy rule base using the subtractive clustering method, we try to eliminate the drawbacks of this method, namely information redundancy, which is similar fuzzy set. This is the key idea of our contribution, as redundancy increases the complexity of the model and complicates the linguistic interpretability of the system. To determine the similarity between fuzzy sets, we can measure the overlap of their membership function. Thus, we can merge the most similar fuzzy sets using the Jacquard's similarity measure. After fuzzy set merging, we may obtain a rule with the same premise part, which is redundant rules. So we merge it by keeping the premise part and averaging the linear parameters of the redundant rule using this formula. To summarize, this algorithm explains the process of the fuzzy rule simplification. So, after generating initial FIS using subtractive clustering method, we apply some operations. First, for each input variable in FIS, we compute the similarity value between each pair of fuzzy sets. Next, we select the pair of fuzzy sets with the max similarity value. If Smax is above the threshold, we merge the similar fuzzy sets by computing the new membership function parameters of the resulting fuzzy set. After that, we update the premise part of rule base using the new fuzzy set. We repeat the instruction while Smax is above the threshold. After merging the fuzzy sets, we simplify the rule base by merging rules whose premise parts are identical. Finally, we obtain a FIS with a simplified rule base. After rule-based simplification, we start the learning phase to adjust the premise and learning parameters of each FIS. For this, we use a hybrid learning strategy according to ANFIS architecture. That is the least mean square algorithm to minimize the RMSE represented in the equation 1. In the backward pass, we use the gradient descent to adjust the premise parameters using the equation 2. In the forward pass, we use the LSE to determine the linear parameters. Now, let's move on to the results section. To generate the dataset for modeling and learning phase, we use our expertise-based guidance technique recently published. Using this method, we generate a dataset of 18,748 data pairs. To start our strategy, we use the subtractive clustering method to generate several FIS based on different radius values. Thus, we obtain the results described in this table. By taking 4 clusters radius, we get 4 FIS with different characteristics regarding the number of rules and fuzzy sets per variable. For example, using a radius of 0.3, we get a FIS of 9 rules and 9 fuzzy sets per variable. We also note that as the radius value increases, the number of rules and fuzzy sets decrease. After that, we execute the rule-based simplification algorithm on each FIS obtained in the previous phase. Using different similarity thresholds, we get various FIS with different characteristics regarding the number of rule and fuzzy sets. From this result table, we note that the number of fuzzy sets is reduced, the number of rules is decreased by 1, and the number of parameters is also reduced. So we can confirm that the complexity of the model is significantly reduced using the rule-based simplification algorithm. But what about their accuracy? So, to improve the accuracy, we have adjusted the parameters of the resulting FIS using the hybrid learning of the ANFIS model. For example, these figures show the curves of the training RMSE and the validation RMSE in 3000 epochs for the case of the FIS with R equal 0.5 and ST equal 0.85. After applying the learning phase on each FIS, we obtain the results depicted in this table. Now, we should evaluate the resulting FIS to balance the accuracy complexity trade-off. Applying our strategy, we produced different FIS with low complexity and high accuracy. According to this table, the FIS-based controller designed with the parameters R equal 0.5 and ST equal 0.85 provides an acceptable number of fuzzy sets and a minimum value for RMSE. This is therefore the controller that best respects the accuracy complexity trade-off. Using the evaluated controller, we have achieved the following elements: reactive navigation in unknown environments, safe navigation by avoiding obstacles, efficient navigation by reaching the target, smooth navigation by performing near optimal path. To evaluate the performance of the mobile robot navigation controller based on the proposed strategy, we have performed a comparison with other state-of-the-art ANFIS controllers in terms of accuracy. So we have compared the traveled path in the benchmarking environment. As depicted in this figure, our controller performed the shortest path to reach the target. We also compared our controller with other state-of-the-art ANFIS controller in terms of complexity. According to the result table, the proposed strategy achieved an optimized FIS of 5 rules and 47 parameters, making it the least complex compared with other controllers. Consequently, the strategy achieves very encouraging results by combining several techniques and balancing the accuracy complexity trade-off. I'd like to conclude this presentation by summarizing the information. In this work, we have proposed a strategy for modeling an ANFIS-based controller for mobile robot navigation. This strategy is based on a suite of techniques designed to balance the accuracy complexity trade-off, and the resulting controller has demonstrated its performance in terms of accuracy and complexity through simulation experiments and comparison with state-of-the-art methods. In the future work, we have decided to address the problem of navigation in more complex environments with specific configuration, adopt distributed and collaborative approaches to develop cooperative controllers for robot fleets capable of navigating within shared environments. And we have decided to implement solution and embedded platforms for real-time navigation applications. And thank you for your attention.